And everybody thinks I'm crazy at first. And maybe I am, but it works. All right. And when I interviewed at Hack 8 years ago, this is the lesson I taught. And I think when I started, they thought I was nuts. And then by the end, I had the job. So, hey, whatever, maybe I was the only person that applied too. I don't know, right? You never know. But here we go. I'd like you to balance this reaction. As my wife opens the garage door, I don't know if y'all can hear that. This is the room above my garage. This is the one day a year where I don't have the air conditioning on or the heat on. It's like I get one class a year where the room is at a pleasant temperature. Next week I'll probably have the heat on, and usually I'm dying up here if I don't have the air conditioning on. So let's balance this reaction here. Hopefully you can tell from my hieroglyphics what I'm trying to do here. We're making bikes. Okay, this would be like a synthesis reaction. Okay, so let's see if we can balance this thing. So obviously this is going to get a what?
A 2.
A 2, right? 2 wheels, 1 frame makes 1 bike, right? You don't need the ones. You don't want to. Okay, great. So we're going to start by doing what's called an excess problem. Okay. So this is a situation where we have, like, let's say 18 wheels and an excess of frames. And I want to know how many bikes can I assemble? The answer is 9. It's actually 9.0 if we're getting all sig-figgy. I don't care about the answer. What I care about is the work, right? Of course, you can do this in your head. Now, just wait. When we get to chemistry, you cannot do it in your head. So there is a rhyme and reason. There's a reason that we're doing this, right? Because if you can do this, you can do chemistry. All right. So that's why we're, okay. Let me show you the process of how I'd like to determine if I have 18 wheels and an excess of frames, how many bikes I can make. First thing is, what does this word mean? Okay. I tell my high school students, and I mean it, okay, that they can never ask me what the word excess means. Okay. If one of my high school students asks me what the word excess means, I just kindly ask them to pack up all their stuff and get the hell out of my classroom for the day. Okay. And I am not joking. I will throw them out. Okay. The reason I have to do that is because if I don't put my foot down and say, you cannot ask me what the word excess means, a kid will ask me what the word excess means every single day, right? And then I'll quit teaching and they won't have a teacher anymore. Okay. So excess, it means more than enough. It means so much that you don't have to worry about. Don't worry about it. I'm not a dictionary. I'm not a thesaurus, right? If you don't know what the word excess means, look it up, right? Essentially, it means you can ignore this thing. You are going to find that that is the most beautiful word in the English language, because by the end of the night, I'm taking that word away. And then that's called a limiting reactant problem, and they suck. Okay, but the word excess is beautiful. It means half the work. It means I have so many frames. In fact, if y'all are smart, it means I've got like 10 or more, right? Okay, but I have so many frames, I ain't got to worry about it. My wheels are going to be what determines how many bikes I can make. Okay, excess problems you're going to find are just half the work. Okay, so what I'm doing here is I'm going to take 18 wheels over to bikes, but you know how we do math? We do math with dimensional analysis. So the way that we're going to set this up is we're going to take this 18 wheels and we're going to put it over 1, right? That's what we've always been doing. But now what we can do is we can use the coefficients from the balanced chemical equation, in this case, the synthesis reaction. We can use the coefficients from the balanced equation to jump from one thing to another. So the way this is going to work is wheels are going to go on the bottom because I want to get wheels to go away. And I'm trying to jump over here to bikes. And this is where the coefficients are going to allow me to figure out the ratio of these parts or of this reactant to this product. There are 2 wheels to every 1 bike. So 18 divided by 2, I could make 9.0 bikes. Now we could get into a philosophical debate. Do I really need the 0.0 in there? How did you determine there were 18 wheels? You probably counted them, so it's not really a measurement, blah, blah, blah. I don't care. Okay, so anyway, 9.0 bikes. Okay, look at the process that we did here. Okay, we used dimensional analysis. We got units to still cancel out, and we used the coefficients from the balanced equation to jump from one thing to another. We are going to have an analog to this in chemical reactions, okay? And the analog to this is going to be called a mole ratio. Okay, in a real chemical equation, you can jump from one thing to another when you are in moles. Okay, that's probably the most important thing that's going to come out of my mouth tonight. We're going to come back to the bikes a bunch tonight. Don't you worry about that. But let me write down what I just said, and then let's do one of these for real. You can jump from one reaction component to another when you're in moles. You have to be in moles before you can go from one thing to another, because moles is the SI unit for amount. It's the SI unit for amount. Grams, because every atom has a different mass, you can't go right between. You have to go to moles first, and then I can go from moles of one thing to moles of another. Okay, so we're going to start out with like the easiest kind of problem, and then we'll go from there. So now, real deal. I'd like you to balance this real chemical reaction. Take a second, balance that one, that real reaction there. So here's how I balance it, right? Okay, 2 nitrogens, I'm gonna pop a 2 there. Remember, big tip number 1, save hydrogen oxygen for last. We're gonna balance the nitrogens first. Now I have 6 hydrogens, I'll pop a 3 there. You don't have to put anything there, but you're welcome to put a 1. If you leave it blank, I assume it's a 1. So now what I'd like to do, we're going to do the easiest kind. This is called reaction stoichiometry. Okay, stoichiometry is the term, what I like to define it as is the math of chemistry. Math of chemistry. So I call what we had been doing before when we were using our chemistry toolbox, I call that simple stoichiometry. But this is now going to be stoichiometry involving a reaction. So we call this reaction stoichiometry. We're going to start with the easiest kind of reaction, stoich, and we're going to branch out from there. We'll start with moles. So let's say I have 3.50 moles of N2, and I have an excess of H2. I want to predict how many moles of ammonia, NH3, that will allow me to make. Now, this is as easy as reaction stoich gets, because this is a mole-to-mole conversion. And this is going to be a one-step problem. You can jump from anything in a reaction to another thing in a reaction if you are in moles, but only if you're in moles. So this is great. I'm trying to go from moles of this to moles of this. This is going to be a one-step problem. I'm going to take 3.50 moles of N2. I'm going to pop it over 1. And now, since I'm in moles, I can use the coefficients from the balanced equation to create what's called a mole ratio. So my mole ratio is going to work like this. I need moles of N2 to cancel out. And I want to end up in moles of NH3. And then what goes in front of these is the coefficients from the balanced equation. So in front of the moles of N2, N2 has a 1. We're going to pop a 1 there. And in front of the moles of NH3, NH3 has a 2. We're going to pop a 2 there. And you can see my moles of N2 have canceled out. And essentially, I'm just going to multiply. 3.50 times 2, that's going to be 7.00 moles of NH3. So if I allow 3.5 moles of N2 to react with an excess of hydrogen, I would be able to make a maximum of 7.00 moles of NH3. You are starting to become chemists, right? Okay, or at least what I like to think of as like synthetic chemists, what a synthetic chemist does. A synthetic chemist makes stuff for people, and you're learning now how to make stuff for people, and that's where reaction stoichiometry comes into play. Now, this is the easiest kind of reaction stoich problem because you started in moles and you ended in moles. So let's kick it up a notch. I have the luxury of a whiteboard. Yes, it is awesome. So I'm going to keep the same reaction, all right? But now let's switch it up a little bit. Let's maybe say I don't know. Let's say we have 12.5 grams of N2, 12.50 grams of N2. Let's say again we have an excess of hydrogen gas. And then let's not go crazy yet. Let's just say how many moles of NH3 do I want to make? So here's how this works. We're going to start by taking what we have, and that's the 12.50 grams of N2. We're going to pop that over 1. Now, I would love to jump from here to here. That's my goal. I want to go from here to here. But I cannot jump from one thing to another until I'm in moles. Got to be in moles before you can jump. I'm not in moles. I'm starting in grams. We got to fix that. How do I get out of grams of N2 and turn it into moles of N2? Think about that for a second. Anybody? How do we get, what's my first step? They gave me this giant mug when I got the job at Penn State Berks to teach OChem lab there. I'm not a Penn State fan, I'm a Michigan fan, but I love this mug. Excellent, Chris. Thank you. Molar mass. We need the molar mass of N2. So if you find nitrogen weighing in at 14.01, but you got 2 of them, that's a molecular weight of 28.02 grams per mole. Now, let's think about it. Take a second. Do I want to multiply by 28.02 grams per mole, or do I want to divide by 28.02 grams per mole? What are we thinking? Multiply by 28.02 or divide? Thank you, Heidi. We want to divide. The 28.02 grams is going on the bottom. The 1 mole of N2 is going on the top. And now I'm in moles of N2. Why did I want to get into moles of N2? Because once I'm in moles, now I can jump, right? Now I can go whoop, jump over here using a mole ratio. So moles of N2 are going to go on the bottom. Moles of N2 go on the bottom. Moles of NH3 are going to go on the top. Moles of NH3. And then the N2 gets a 1. And the NH3 gets a 2. And now we're going to do 12.50 divided by 28.02 times 2. And with 4 sig figs, you'll find this would allow me to make 0.8922 moles of NH3. I can make 0.8922 moles of NH3. So we're getting there. Y'all are getting there. Absolutely getting there, right? We're getting close to what would be like a real problem that we would like really, really do in the real world. How are we feeling? Feeling okay? Well, I'll tell you what, let's do it. Let's do our first real problem. This problem here would be this would be like if you were a synthetic chemist, you would do this kind of problem all the time. Let's do it. Let's get a new reaction. Let's get a fresh reaction going here. Yeah. Oh, I don't know. Let's do another synthesis reaction. Go ahead, bounce that one. All right, so we got 2 oxygens. We're going to pop a 2 there. 4 hydrogens. We pop a 2 there. There we go. So I don't know. Let's say I don't know, let's say that you're working on a hydrogen fuel cell, which is what this would be. A hydrogen fuel cell would take hydrogen and oxygen gas, combine them to make water. And let's say your goal is to make 5 grams of water, 5.00 grams of water. So my first question would be, all right, well, how many grams of O2 do I need to put in there to allow to mix with an excess of hydrogen or whatever, to allow to mix with hydrogen in order to get 5 grams of H2O? So in this problem, again, we're trying to jump from one thing to another. In this problem, we're actually going in the reverse direction, which is usually how a lot of synthesis problems work. So we're saying, I want to make 5 grams of product. How many grams of this reactant do I need to put in there? Which again is what you'll generally find yourself doing. If you're a synthetic chemist, your boss will usually get an order for whatever, 5 grams of this product. And then your boss will come to you and say, hey, make me 5 grams of this stuff. And you got to figure out how much of each reactant to put in there to make your boss 5 grams of that stuff, right? So they can send it off and make a bunch of money and, blah, blah, blah. So here's how this is going to work. We take what we're given, and we need to write the identity of it, because again, it's going to be important for the mole ratio. So people get in a bad habit, they'll just do 5.00 grams and put it over 1, but you got to tell me it's 5.00 grams of H2O. So we're going to start with 5.00 grams of H2O. We're going to put that over 1. My goal is to jump from here to here, but I cannot jump from here to here until I'm in moles, right? So my first step, if I'm in grams of H2O, what do I need to do before I can jump? What's my first step going to be if I want to go from here to here, but I'm not in moles?
Molar mass of H2O?
Yeah, we're going to divide by that molar mass of H2O. So you need to add up the molar mass of H2O. Go ahead, take a second and add that up. So 1.01 times 2 plus 16, water should weigh in at 18.02 grams per mole. Now I want you to think about, do I want to multiply by 18.02 or divide by 18.02? Take a second. Why don't you write the first step in there? Hopefully you figured out that you are going to want to divide by that. That's how we're going to get the grams to cancel out. So 18.02 grams of H2O are in a mole of H2O. So now we're in moles of H2O. And now I can jump, because once you're in moles, you can jump. So now I can do a mole ratio. Moles of H2O on the bottom, moles of O2 on the top. The H2O is going to get a 2, and the O2 is going to get a 1. But I'm not done. If I had said, how many moles of O2 do I need? Then I would be done. Equals done, right? But I didn't. I said, how many grams of O2? So what do I do now? I'm in moles of O2. How do I turn that into grams of O2?
Molar mass of O2.
I need the molar mass of O2 now, right? So I went from grams of H2O using H2O's molar mass. Then I went from moles of H2O to moles of O2 with the mole ratio from the balanced chemical equation. Now that I'm in moles of O2, I can go to grams of O2 using the molar mass of O2. So we just add that up. 16 times 2 is 32.00 grams per mole. I want you to think, do I multiply by 32.00 or divide? Go ahead and put that final step in there. Hopefully you're seeing that you should multiply by the 32.00 grams per mole. And now you're done. Now you can grab your calculator. So 5.00 divided by 18.02 divided by 2 times 32. And with 3 sig figs, you should get 4.44 grams of O2. This is the kind of stuff that we chemists do all the time. If I want to make 5 grams of H2O, then I need to put in 44 or 4.44 grams of O2. Now, I'll tell you what, let's figure out how many grams of H2O that we need to put in there. Now, if you're smart, you're hopefully thinking law of conservation of mass, you wouldn't actually have to do any work, but I'm going to save that. If you don't see that, it's fine. We're going to do that. We're going to do this the hard way, then we'll do it the easy way. And we can only do the shortcut that I'll show you at the end because this is a synthesis reaction. You can only take shortcuts with synthesis and decomposition reactions. So we'll talk about that in a moment. But let's change the problem now. I'm going to keep this all up here, but now I want to know, hey, all right, I need 4.44 grams of O2 to do this, but I want to now go from here to here. All right, so if I need to put in 4.44 grams of oxygen, how many grams of how many grams of H2 do I need to put in there? So we're going to take this 5.00 grams of H2O again. Now this time I'd like to jump from H2O to H2. So again, I need to be in moles before I can do that. So it's going to be the same first step. We're going to divide by the molar mass of H2O, 18.02 grams of H2O in a mole of H2O. But this time, we're going to have a different mole ratio. We're going to have moles of H2O on the bottom. We're going to have moles of H2 on top. The H2O gets a 2, and the H2 gets a 2. I'll let you kind of catch up, following along here. Okay, again, now we're just going to the other reactant. So grams of H2O gone. Now we're in moles of H2O. Now we can jump, mole ratio, moles of H2O to moles of H2. But I want grams of H2. So now I need the molar mass of H2. So if you find that, 1.01 times 2, that's 2.02 grams per mole. And I'm going to want to multiply by that, 2.02 grams of H2, 1 mole of H2. So we're going to pop that in, 5.00 divided by 18.02. Times 2 divided by 2. If you're smart like me, I don't put anything in. That's 1. Right now, I need to see that. Okay, but I don't actually hit times 2 divided by 2. That would be redundant. Anyway, so if you do that correctly, you should get 0.560 grams of H2. Now, for this reaction, because it was a synthesis reaction, there's actually a shortcut. We could have gotten that 0.560 grams much faster. What's the faster way that we could have got that with no reaction stoichiometry?
Subtract the last question from 5.
Yeah, very good. Because of the law of conservation of mass, we know that mass cannot be created or destroyed. So because this is two things making one, we know that this has to add up to 5.00. So once we got the 4.4, essentially what we had is x plus 4.44 equals 5. It's 0.560. We could have got there. We could have just subtracted. If you don't see that shortcut, that's fine. In honesty, you can't do that shortcut most of the time. You can only do that shortcut if it's a synthesis or decomposition reaction. If there was another product over here, let's say there was another product, then you couldn't do it because I know this, but I don't know the mass of the other one. So you can't do that law of conservation of mass shortcut. Look out for it. You know, if it's there, it's fine. Let's try a double replacement reaction with one of these, okay? And let's go back and do an excess problem, right? Which is what we started this with. Oh man, I don't know. Let's do, yeah, let's do this guy. Let me copy that down real quick. So we got iron 3 chloride plus potassium hydroxide goes to potassium chloride and iron 3 hydroxide. That got a little messy. Let me clean that up. There we go. Might take a second to balance that first. You need the practice. I don't. All right, so 3 chlorines, you pop a 3 here. This is where I like to use big tip number 2. Big tip number 2 says keep polyatomic ions grouped together. We've got a hydroxide here and a hydroxide here. So if you recognize the same polyatomic ion on both sides, you can take a shortcut. There's 3 hydroxides, so I'm going to pop a 3 there, 3 potassiums, 1 iron, 1 iron. That's now balanced. It's a 1, 3, 3, 1, the way we wrote that. Okay, great. So let's go back to an excess problem. Let's say, I don't know, let's say we have an excess of iron 3 fluoride. Or let's say we have 8.15 grams of potassium hydroxide, and I want to know how many grams of iron 3 hydroxide could we make with this. Again, this is the kind of thing chemists do all the time, sort of synthetic chemists would do. Your boss comes to you and says, hey, I got an order in for iron 3 hydroxide. I want you to make as much of it as we can. We need to ship it out to the client ASAP. So you go to the back and you realize we got a whole crap ton of iron 3 chloride, just got a big old jug of it, right? So we're just going to dump that in there. It's going to be an excess. But we realize we only have 8.15 grams of potassium hydroxide left on the shelf. So we're going to take that 8.15 grams of potassium hydroxide. We're going to allow it to react with more than enough iron 3 chloride. And we want to predict how many grams of iron 3 hydroxide we can make. This is the stuff that chemists do. It's what we really do. Okay, it's what we do for a living. All right, unless you're an analytical chemist, you don't really, you know, you're just quality control. But if you're a chemist who makes things, it's what you do. Okay, so we want to go from here to here. All right, so we're going to start 8.15 grams of KOH over 1. Now I would like to jump from here to here, but I cannot jump until I'm in moles. Okay, cannot jump until I'm in moles. So I need to get rid of grams. I want you to see if you can, I'll tell you what, I want you to see if you can do this. Why don't you see if you can do it from start to finish? Okay, think about what you need to do to get from here to here. I'll give you like, I don't know, 3 minutes or so, right? Again, if you get stuck, we're gonna go over it. It's all right. All right. So we are trying to jump from here to here. And before we can jump from there to there, we got to be in moles. So we're in grams of potassium hydroxide. So the first thing we need to do is get the molar mass of potassium hydroxide. So 39.1 plus 16 plus 1.01 should be 56.11 grams per mole. Now we have to decide, do we multiply or divide by 56.11? Well, since we need grams to cancel out, your first step should be dividing by 56.11 grams of potassium hydroxide for 1 mole of potassium hydroxide. First thing, look at what you did. Is that the first thing you did? If it's not, the train probably came off the tracks right there. Okay. Next, now we're in moles of potassium hydroxide, and since we're in moles, now we can jump. So this is where we want to do what's called a mole ratio. So the moles of KOH are going to go on the bottom because I need the KOH to cancel out. And moles of iron 3 hydroxide are going to go on the top because we want to end up in that. The KOH is going to get a 3 and the iron 3 hydroxide is going to get a 1. So now we're in moles of iron 3 hydroxide, but I want to be in grams of iron 3 hydroxide. So now you have maybe the hardest part, and that's getting the molar mass of that iron 3 hydroxide. So we need to add that up. Here's how we're going to do that. We have an iron, so that's 55.85. And then you have to distribute this 3. We have 3 oxygens, so plus 3 times 16. And then we have 3 hydrogens, so plus 3 times 1.01. That's 106.88 grams per mole. Now, I'm going to want to multiply by that 106.88 grams of FeOH3. Okay, I want to multiply by that to end up there. So take a look at your work. First step, divide by the molar mass of potassium hydroxide to get us to moles. Then it's a 3-to-1 mole ratio. And then in the last step, you're multiplying by the molar mass of iron 3 hydroxide to get there. So 8.15 divided by 56.11 divided by 3 times 106.88. I get 5 point, looking like 3 sig figs, 5.17 grams of iron 3 hydroxide as my theoretical yield there. How many people got 5.17 grams of iron 3 hydroxide? Hey, all right. If you didn't get 5.17 grams of iron 3 hydroxide, do you see where you went wrong? Was it a molar mass that was wrong? Again, I've been doing this 13 years. I would guess that some people got that molar mass wrong. So the first thing, 3 oxygens, 3 hydrogens, people forget to distribute theirs. So, did you have the process down right? That would be important. Okay, well, we have a term for this. This number, you're going to want to write this down. This is called the theoretical yield. The theoretical yield is the mass of the product, okay, that you should be able to make in theory. This is like assuming the reaction goes completely as it's supposed to, assuming the reaction goes perfectly. This is the maximum amount of product you should be able to make. So the theoretical yield is the maximum amount of product you can make. Maximum amount of product you can make. Here's the thing. In the real world, you like never get that, ever. Okay, ever get that. Hang on, Ethan. Ethan, what? So Ethan's got to go like, what do you think the issue? So here it's this potassium plus oxygen plus hydrogen on the periodic table, the average atomic mass. I mean, do you see how to get them?
Yeah, I get those names. It's just the actual number.
Like where to get the numbers from?
Yeah, like how to find it, like what.
Oh, so those come off of the periodic table. They're the average atomic masses on the periodic table. So to get that 56.11, you need this average mass of potassium, 39.10. Then you need an oxygen, 16, and you need a hydrogen, 1.01. So that's where that 56 comes from.
Okay, gotcha.
So this theoretical yield, this is the maximum amount of product you can make. Okay. In the real world, you like almost never, ever get that. You will always get something less than that. Okay. What you get when you actually do the reaction, that's called the actual yield. So let's say you're a chemist, you set this up on paper. I should be able to get 5.17 grams of iron 3 hydroxide. So let's say you actually set this up, and let's say you do it, you collect the iron 3 hydroxide, and let's say your actual yield is 4.85 grams of iron 3 hydroxide. So you set this up, you do it in the real world, you're supposed to get 5.17 grams of iron 3 hydroxide, but things never go as planned. And you get less than that. Almost every time you will get something less than that. You will almost never actually get the theoretical yield. So now we chemists have come up with a way to evaluate how good a reaction is by comparing the actual yield to the theoretical yield. This is called percent yield. You're going to have to memorize this equation. Okay, the percent yield for a chemical reaction is equal to the actual yield divided by the theoretical yield. And then since it's a percent, you multiply by 100. So this is a very important equation for chemists. You'll use this in every chem lab, from here on out in your chemistry labs, okay? Because this is how chemists evaluate how good their reaction is. Actual yield, which you actually got, divided by the theoretical yield, what you were supposed to get, times 100. Now, the highest percent yield you should ever get would be 100% yield. You should never get above 100% yield because that means you just created matter, right? So let's figure out the percent yield for this reaction. If we do this reaction and we get 4.85, but we're supposed to get 5.17, let's find the percent yield. So the percent yield for this reaction would be that 4.85 divided by the 5.17 times 100. That'll give us our percent yield here. 4.85 divided by 5.17 times 100. This reaction, and I don't grade percents for sig figs, this reaction would have a percent yield of 93.8%. 93.8% yield. People always say, is that good? Well, it totally depends, right? If you are a synthetic organic chemist, you are usually shooting for above 95. Okay, we could talk about why in a minute. But it totally depends on what you're doing. Totally depends on what you're doing. Yeah. How are we feeling? Let's try another involved one, and then maybe we'll take, like a break. Let's try, let's try another good one here. Guess we could try a single replacement reaction. Let's try this. First thing, can you name these compounds? That would be a good review from Unit 2. Can you identify that polyatomic ion? That would be a good one. If you can't, you need to study those polyatomic ions that we talked about at the beginning. This would be silver nitrate, and that would be zinc nitrate. Great. So, oh man, I don't know. Let's say, boy. Let's say you have a excess of silver nitrate. Let's say you add 2.5 grams of zinc. And I want to know how many grams of silver could you precipitate out? Go ahead, give that one a shot.
Is that a 5 or a 3 under zinc?
That is an S. So that's
that's-
solid zinc. This is an aqueous solution. That's an AQ. This is an aqueous solution, and that's an S for solid. So the states of matter don't impact it. Essentially, this should allow you to visualize what's happening. Okay, excellent question there about the states of matter. So this is saying you have silver nitrate dissolved in solution. It's an aqueous solution. You're going to drop a solid piece of zinc into here. Okay, so the zinc goes in. The zinc is going to dissolve, and silver is going to crash out. So the silver is going to come out as a solid. These states of matter just allow you. So imagine this zinc going in, dissolving, and then silver coming out. Yeah. So I'd like you to try and go from here to here. Give it a shot. Two nitrates, got to put a 2 there. 2 silvers, got to put a 2 there. So hopefully the first thing you did was balance this, right? So next, we're going to do 2.50 grams of zinc. I guess first of all, do we need anybody more time? How would again impossible for me to judge over Zoom. Are we good? I don't know what the answer is. I just make these up. We're gonna find out though. All right, I'm seeing thumbs up, so we're going for this thing. So now we need to go from grams of zinc to grams of silver. So we're gonna need to use the molar mass of zinc, which I think is 63.55, but that's actually one that I don't have committed to memory. 65.38, dang it. 65.38, so 65.38 grams of zinc on the bottom, 1 mole of zinc on the top. Now that I'm in moles of zinc, I can go into a mole ratio. 1 mole of zinc creates 2 moles of silver. 1 mole, 1 mole of zinc creates 2 moles of silver. And now that I'm in moles of silver, I can use the molar mass of silver, which is 107.87 grams of silver to 1 mole of silver. And now we can punch that in our calculator. So 2.5 divided by 65.38 times 2 times 107.87. That's 8.25 grams of silver, which I think I saw. Yeah, there you go. A couple people. That's fantastic. Very nice. Very, very well done, everybody. Very good. Real quick, let's get a percent error here before we take a break. Let's say you do this. And let's say only 6.15 grams of silver is formed. I would like you to calculate a percent yield for this reaction. Go ahead. All right, so percent yield is the actual yield, 6.15 grams, divided by what you were supposed to make according to the math, 8.25 grams, and then times 100 to make it a percent. So this has a terrible percent yield, 6.15 divided by 8.25 times 100. This is nothing to write home about. This is a 74.5% yield reaction. Not so good. Why do chemists shoot for above 95? Here's why. If you're a synthetic chemist, especially a synthetic organic chemist trying to make pharmaceuticals, that is often a multi-step reaction, meaning that to get to the final thing you want is multiple steps. So like you start with reactant A, and that makes B, and then you change B into C, and then you change C into D, and then you change D into E, and maybe after a 1, 2, 3, 4-step reaction, you're there. But sometimes it's crazier, right? There are some crazy drugs like the one that jumps out of my mind, Taxol. It's a chemotherapy drug. It is 22 steps to make that thing. And the reason that we shoot for above 95% yield is because when you have multiple reactions, anything below 95% really kills your overall yield. Here's how it works. Let's say every one of these steps was 95% yield, 95, 95, 95%, and 95%. The overall reaction yield, so each one of these steps is 95. The overall yield can be found by multiplying them all together, right? So if I take 0.95 times 0.95 times 0.95 times 0.95, that'll give me my overall yield. 0.95 times 0.95 times 0.95 times 0.95. That is an overall yield of 81%. So even though each reaction had a yield of 95% and you only lost 5% of product every time, it was compounding. And you only, with 4 reactions at 95%, 81% yield. That's why you really cannot have a reaction drop below that 95% yield.